So, how does what we know about the diversification of sulfur metabolism match up to the isotope record? The aforementioned UV photolysis of sulfur dioxide will produce elemental sulfur and sulfate aerosols, which will then rain down into the oceans. Much of the pyrites from the Paleoarchean with highly negative delta 34s values also have positive cap delta 33s values. This suggests the majority of sulfur used by contemporary microorganisms was elemental sulfur. When did the advent of elemental sulfur reduction come into the picture? Thiosulfate reductase and polysulfide reductase are homologous enzymes, but when placed on a phylogeny, thiosulfate reductase are paraphyletic, while polysulfide reductase are monophyletic. This means that all polysulfide reductase enzymes descend from a single common ancestor, while the common ancestor of all thiosulfate reductase enzymes also gave rise to the ancestor of polysulfide reductase, strongly implying that the progenitor of polysulfide reductase reduced thiosulfate. Although polysulfide reductase can't directly metabolize elemental sulfur, sulfide ions will react with elemental sulfur rings, breaking them open and forming a polysulfide. So, while elemental sulfur reduction is the first form of sulfur metabolism attested in the geologic record, it's likely that sulfite and thiosulfate reduction preceded it. Another curious feature is that in the Eoarchean, sulfides subjected to UV photolysis fall on the Archean reference array, but in the Paleoarchean, they fall on the 193 nanometer array. This suggests that there are high levels of carbonyl sulfide in the atmosphere, which absorbs most UV light except at 193 nanometers. What factors can explain the discrepancy between the molecular and geologic record? Part of the discrepancy between the geologic and molecular records can be explained by the emergence of another key metabolic process, photosynthesis. The oldest evidence of photosynthesis dates from about 3.5 billion years ago, around the same time we find evidence of sulfur metabolism. More specifically, we found fossilized stromatolites and filamentous microfossils in the Strelley Pool Formation located on the Pilbara Craton in Australia. Stromatolites are microbial mats formed when sand and dust gets caught in a gelatinous microbial biofilm and becomes cemented. The reason these stromatolites are believed to have been formed by photosynthetic organisms is that the carbonates in what would have been the photic zone are depleted in carbon-13. This means that the carbon was likely used to produce organic matter by photosynthetic organisms and was then remineralized by respirers as carbonate. Furthermore, gypsum from similar aged rocks has delta 34s values close to 0, suggesting that these organisms used hydrogen sulfide as the electron donor, producing sulfate in a process known as photothioatrophy. Similar traces of photosynthetic organisms are found in Kapval, South Africa, from 3.25 billion years ago. It should be noted that banded iron formations, or BIFs, and stromatolite-like structures have been found from the Eoarchean, and these are hypothesized to have been produced by photosynthetic organisms, but these claims have largely been discredited. But how did photosynthesis itself come into being? Photosynthetic organisms harness light energy using large protein complexes known as photosystems embedded in the membrane. This is accomplished by metal porphyrin complexes in the photosystem known as chlorophylls, which absorb light and use it to excite electrons in the reaction center, which then flow down the electron transport chain. The progenitor to the first photosystem, which we'll call PSA, is hypothesized to have been a membrane protein which was part of a respiratory electron transport chain, while the chlorophylls were once serohemes that facilitated electron transfer. At some point, this respiratory complex was struck by light, and the sudden input of a product, energy, reversed the direction of the reaction, reducing carbon while oxidizing another molecule. As discussed before, the geologic record indicates that the initial electron donor was likely hydrogen sulfide, and this is reinforced when we look at the molecular evidence. Although the oxidation and reduction of elements like iron and oxygen are carried out by non-related enzymes, the oxidation and reduction of sulfide and sulfate are carried out by homologous versions of DSR, adenyl sulfate reductase, or APR, and sulfate adenyl transferase, or SAT. Furthermore, reductive DSR enzymes are paraphyletic, while oxidative ones are monophyletic, indicating that these were likely initially used in respiration. Finally, when we look at the phylogeny of APR enzymes, the split at the base of the tree is between the oxidative and reductive versions, implying that the advent of photosynthesis came shortly after the addition of sulfate as an electron acceptor, and that the first photosynthesis was a reverse sulfate respiration pathway.
Chlorophylls are used by modern photosynthetic organisms, which produce oxygen, but anoxygenic photosynthesizers, those that use another electron donor, use bacterial chlorophylls, which are structurally intermediate between chlorophylls and respiratory serohemes. Virtually all of these photosynthetic pigments possess a magnesium ion in the center, but the heme group, which ultimately gave rise to them, might have had a zinc ion instead. This is because electrons in zinc can remain in an excited state for longer periods of time when struck by light, giving more time for an electron carrier to take said electron. Bacterial chlorophylls have two absorption peaks, one in the long UV wavelength range and the other in the near infrared. This has led to speculation that these were adapted to the Archean solar irradiance regime, where the cooler temperature of the surface of the sun would produce more infrared light, and the lack of an ozone layer allowed UV light to inundate the surface. Basically, these pigments both harvested energy and provided UV shielding. Some astrobiologists have argued that the high levels of UV light would have killed any early organism trying to carry out photosynthesis before photoprotective pigments could evolve. They argue that instead of using sunlight, these organisms used infrared light emitted by volcanic vents. In deep sea black smokers, the intense pressure increases the boiling temperature of water, allowing it to remain liquid at 400 degrees Celsius. And at this temperature, the peak emission wavelength is roughly the same as the infrared peak in bacterial chlorophylls. However, the problem with this is that since water absorbs infrared light, the total light energy available from hydrothermal emissions is less than what would be available from sunlight at a kilometer deep. At this depth, any UV light would have been absorbed, making the notion that the first photosynthetic organisms used light from volcanic vents very unlikely.
So, what sort of environmental impacts would the origin of photosynthesis have had? In volcanic vents where sulfur metabolism is common, between hydrogen sulfide, sulfur dioxide, and its derivatives such as sulfate and sulfite, and molecular hydrogen, sulfide is the most abundant, while molecular hydrogen is the least. Prior to the advent of photosynthesis, the electron donor used to produce organic molecules from carbon dioxide was hydrogen, so the quantity of organic matter would have always been less than that of oxidized sulfur species. This means that any sulfur-reducing microorganism would have been limited by the availability of electron donors, leaving a large quantity of sulfate in the vent fluid. Furthermore, since hydrogen sulfide is more abundant than oxidized sulfur species, an even smaller fraction of the hydrogen sulfide in the vent fluid will have been biogenic. This will effectively dilute any isotopic signal from microbial sulfur reduction. Indeed, when we look at sulfite in modern vent fluids, there is no isotopic signal characteristic of biotic activity, even when we know there are sulfate reducers inhabiting the vent. However, once photosynthesis came into the picture, hydrogen sulfide limited how much organic carbon could be produced. This would have also produced sulfate, but the high concentrations of barium in the ocean would cause it to drop out as barite, making it difficult for sulfate reducers to access. This would lead to a situation in the periphery of the vent where sulfate reducers were electron acceptor limited. This would have selected for organisms which could use other sources of sulfur, such as elemental sulfur, as an electron acceptor. This would also explain why elemental sulfur reduction appears to come first in the isotopic record, in contrast to what the molecular evidence indicates. This would also give rise to a protocarbon cycle, where producers and consumers would cycle carbon and other biophilic elements between each other, while using electron donors and acceptors produced by geologic processes. Although the nitrogenous enzyme likely evolved around this time, which allowed microbes to convert molecular nitrogen in the air to ammonia and bind it to biomolecules.